Imagine a winding river valley, its currents flowing freely until a master architect arrives. Picture a humble creature ceaselessly dragging branches to reshape an entire watershed. Envision avian artisans weaving intricate nests, cell by cell, knot by knot. Consider tiny engineers sculpting hexagonal wax chambers that defy human imagination. Behold vast termite cities rising from the savanna, complete with living air conditioning systems. What do these marvels reveal about nature's unparalleled engineering prowess? And what lessons do they hold for our own human designs? Welcome to a journey celebrating animal architects and the brilliant structures they build. Our story opens on a misty dawn. A soft light filters through towering conifers, illuminating a quiet stream. Here, the industrious beaver waits patiently, its fur damp with morning dew. We watch as it carefully selects a sturdy branch, grips it with powerful jaws, and hauls it laboriously toward the water's edge. This branch will join countless others to form a complex dam of immense scale. Beaver dams can stretch up to half a mile long and tower more than 17 feet high. Few human engineers attempt such feats with mere sticks, mud, and instinct. Yet each morning and evening, the beaver returns again and again, doubling and tripling the structure until it defies rushing currents. The process unfolds in intuitive stages. First, the beaver scouts sites by sensing subtle changes in water flow and bank stability. It then diverts the stream by building a low barrier, gently reducing flow pressure. Next, it drives interlocking branches and logs deep into the soft mud, creating a triangular cross-section that resists hydraulic force. Into this strong base, it weaves sticks, bark, rocks, and clumps of mud, forming a sealed superstructure that holds back the river's energy. On one side, water pools into a calm, protected pond. On the other, the current flows unhindered downstream, preserving the river's natural path beyond the dam. Within the subterranean lodge nestled at the pond's center, the beaver family remains safe from predators. The lodge features underwater entrances that only the residents know how to navigate. Beneath a frozen surface, kits practice swimming in the icy water, guided by their parents. Above, adults forage for fresh bark and branches, hauling them underwater for storage. During lean months, these stored branches provide crucial food and construction material for ongoing maintenance. Under relentless winter pressure, the dam endures freezing, shifting ice, and fluctuating water levels, yet it stands firm season after season. Beavers employ structural engineering principles remarkably similar to those studied in universities. Triangular cross-sections channel force along strategic angles. Interlocking branches distribute pressure evenly, and the blend of mud and bark hardens like reinforced concrete, sealing gaps under cycles of wetting and drying. In the birdie-protected landscape of the Czech Republic, beaver dams restored degraded wetlands, saving local authorities over $1,200,000 in restoration costs. This living case study illustrates how intelligent design by nature can revive ecosystems and benefit human communities. Every stick placed by a beaver reveals resourceful problem-solving. When water levels rise too high, the dam self-adjusts by channeling small leaks that prompt the animals to add more material. During dry spells, the pond recedes, exposing new branches that beavers quickly harvest and reposition. There is no blueprint, no measuring tape, only an intuitive grasp of fluid dynamics and structural resilience. These creatures may lack formal training, yet their instinctive engineering rivals human accomplishments in complexity and durability. Today, conservationists mimic beaver techniques to manage streams and reduce flooding. By installing simple wooden posts and letting nature take its course, humans collaborate with beaver instincts. This biomimetic approach hints at a future where designs harmonize with, rather than conquer, the natural world. We learn to appreciate that our greatest innovations might emerge not from steel mills or concrete plants, but from the quiet labors of a handful of beavers working in rhythm with a flowing stream. As the sun ascends, we drift away from the riverbank toward a stand of swaying palms. Here, high above the ground, another master builder awaits. A male weaver bird begins its work. With a single thin strip of grass, it crafts a secure knot around a slender branch. This tiny strand, 20 to 60 centimeters long, becomes the first stitch in a suspended architectural marvel. The male weaver bird may make up to 500 trips in a single day, each one precise and purposeful. It plucks fresh strips of paddy leaves or coarse grasses, strips them to uniform thickness, then returns to the budding nest. There, it weaves each fiber through opposing angles, tightening knots until the structure takes shape. Over and over, it drills holes, threads fibers, and tugs each strand taut, shifting branches and adjusting tension to maintain perfect balance. In this careful choreography, every movement matters. The nest begins as a small loop. Soon, a spherical shell emerges, its outer form shaped by thousands of knotted joints. The walls thicken with each layer, reinforced at stress points with bundles of extra fiber. Within, a suspended chamber cradles eggs and nestlings. The long, narrow entry tube deters snakes and other predators, offering safe passage to parents, but a treacherous maze for intruders. A potential mate inspects every curve, every opening. If she finds the entrance tube too wide or the chamber too cramped, she rejects it without hesitation. The male may then abandon the half-finished masterpiece and start again from scratch. This selective process ensures only the finest nests earn approval, elevating design standards across generations. For a bird weighing mere grams, this level of quality control rivals human architects who must satisfy demanding clients. Weaver birds teach us about material selection and quality assurance. They test fibers for strength, discard weak strands, and weave redundant layers in critical areas. Such attention to detail echoes modern textile engineering, where fiber orientation and knot strength determine structural properties of advanced composites used in aerospace, architecture, and wearable tech. Our journey soars onward to buzzing fields alive with murmuring wings. Beneath the eaves of a farmhouse, bees converge on a wooden frame. With uncanny precision, they sculpt hexagonal cells from wax secreted inside their own bodies. Each cell measures exactly the right size for storing honey, pollen, or nurturing brood. This hexagonal geometry maximizes storage volume while minimizing building material. Mathematicians have long marveled at the honeycomb's perfection. The shape offers the greatest storage capacity for the least surface area. By joining three edges at precise angles of 120 degrees, each cell fits snugly against its neighbors, leaving no wasted space. The result is a tessellated marvel that supports tremendous weight and adapts seamlessly to the curved contours of a hive. Worker bees collaborate with choreographed efficiency. A single bee can construct several cells in an hour, warming wax with its body heat before molding it with delicate mandibles. Over thousands of cells, the hive emerges as a unified structure, guided by instinct, yet achieving geometric sophistication beyond many human designs. Inside the honeycomb, life thrives in ordered rows. Brood cells house developing larvae, while honey cells store sweet reserves for lean seasons. Pollen cells line the periphery, ready to feed future generations. Ventilation channels regulate temperature and humidity, ensuring optimal brood development. This synergy of architecture and biology underscores nature's holistic approach to design. By performing a waggle dance, forager bees communicate precise locations of nectar sources. This dance dictates thousands of coordinated flights, ensuring efficient resource gathering and construction. The hive functions like a distributed workforce, each individual contributing specialized skills toward a shared objective. No central manager, yet the result rivals the most complex human enterprises. Engineers studying the honeycomb find inspiration for lightweight panels, efficient packing algorithms, and novel heat exchanger designs. From aerospace components to sustainable packaging, hexagonal patterns derived from bees influence countless human applications. In laboratories worldwide, researchers develop micro-electromechanical systems that mimic honeycomb geometry to create materials that are lighter, stronger, and more energy efficient. Beekeepers harvest honey frames carefully, leaving enough reserves for the colony to survive winter. This practice echoes sustainable management principles. Take only what you need and ensure the system thrives for seasons to come. It reminds us that human industry and nature need not be adversaries, but partners in shared abundance. Our final destination lies on a remote savanna, where heat radiates from sun-baked earth. Rising from this landscape are colossal termite mounds, some towering over 6 feet tall. These structures form thriving underground cities, home to millions of individuals working in unison. Their mission is clear: to maintain stable internal climates despite searing days and chilly nights. Termites excavate elaborate passageways and chambers, carving spaces for nurseries, fungus gardens, and food storage. They engineer chimney vents that draw cool air in at night and expel hot air by day. Sun-heated outer walls create convection currents within interconnected shafts, naturally regulating temperature to within a few degrees of perfect comfort. Construction begins deep underground, where workers gather soil, saliva, and fecal matter, mixing them like mortar to form hard, durable walls. They climb upward, shaping external buttresses that shade interior spaces and channel wind flow. The mound's shape, often a steep cone or elongated ridge, maximizes air movement without mechanical fans or solar panels. Inside, chambers glow with diffused light, even though sunlight never reaches them. Fungal farms cultivate essential mushrooms, tended by silent caretakers who prune and transport nutritional blooms. Nurseries cradle eggs and larvae, kept at precise humidity and warmth. Each corridor, each open chamber, serves a distinct function in maintaining the colony's health. Different termite species create diverse architectures. Some build flat-topped mounds with broad bases. Others craft towering spires pierced with narrow vents. In hot regions, mounds remain low but sprawling, maximizing shaded area. Each design reflects a local climate and soil composition, showcasing adaptive strategies across ecosystems. Like human architects designing green buildings, termites balance airflow, insulation, and energy efficiency. Their bioclimatic mounds outperform many modern structures without electricity or metal reinforcements. Researchers have replicated termite-inspired ventilation systems in office buildings, reducing energy costs by nearly 50%. In Zimbabwe, a pavilion modeled after termite mounds hosts exhibitions in natural comfort. In Australia, office blocks mimic termite circulation patterns to stay cool. The social structure of a termite colony is as finely tuned as its architecture. Soldiers, workers, and reproductive castes fulfill specialized roles. Soldiers guard against threats, workers tunnel and cultivate fungus, and reproductives sustain the colony's future. Communication occurs through chemical signals, pheromones, that coordinate thousands of individuals toward a shared goal. As we step back from the termite mound, we see not just soil and saliva, but a living testament to collaborative intelligence. Millions of creatures cooperating to achieve complexity far beyond any individual capability. Their structures blend form and function, echoing the highest ideals of human engineering. Now stand back and witness a grand montage. We revisit the tranquil pond created by beavers, its mirrored surface shimmering in golden light. We soar again with the weaver bird, marveling at the gentle sway of its hanging nest. We peer into the honeycomb, admiring hexagonal cells lined with glistening honey. We gaze upon the termite fortress, its vents and buttresses alive with whispering winds. These scenes remind us that nature's architects work without blueprints, without languages or power tools, yet their creations rival the finest human achievements. Every dam, nest, comb, and mound embodies lessons in efficiency, resilience, and harmony with the environment. They challenge us to rethink conventional design, to learn from instincts honed over millions of years. As our journey concludes, carry with you a renewed sense of wonder and inspiration. The ingenuity of these wild architects reveals possibilities for human engineering yet to be imagined. Let us learn from their masterpieces' works to design's greater sustainability, stronger structures, and deeper respect for the natural world. Marvel at the ingenuity of nature's architects and discover how their creations inspire human engineering.